It is time to calibrate the spectrum analyzer. How are we going to do that? Well, first step, we're going to open the notebook, 8560 calibrate. And then we're going to grab the EEPROM. We'll open a connection to the device and it'll slowly, over GPIB, grab the EEPROM. And while it's doing that, let's talk about the setup. So the setup here is that we have a spectrum analyzer, we have a power sensor, and we have a splitter. The idea is that a signal generator will apply a signal to the splitter, which will then mirror it into the spectrum analyzer and power sensor. And it's a high symmetry device, so it can be constructed with high precision. So we're relying on the symmetry of the splitter and the ability of the power sensor to sense power. Power sensor is rubbish at separating different frequencies, but it's really good at sensing power. And since we're only applying one frequency, that's all we need. And then we'll be able to transfer that really good level characterization from the power sensor over to the power meter. All right, so we're going to sweep the signal generator and then calibrate this thing. Now, the way that we're talking to this is through GPIB, but of course GPIB is that old parallel standard. We're actually talking, the Python code is going to be talking through Ethernet to an Ethernet GPIB adapter, an AD007 from Tektronix, although anything VXC 11 compatible should work, because I'm using the library Python VXC 11, which I like because if you use a USB adapter, then you have to worry about the USB drivers, and those tend to come in big packages, and then they're incompatible with the OS versions, and they're incompatible with virtual machines. They're big and clunky to take around. This is just a tiny little Python library, and all it needs is the ability to connect over a network. As long as DHCP works on your network, this is going to work. You don't need to mess with any drivers, and so I like the Ethernet-based GPIB adapters a lot for that reason. Oh no, it's still downloading an EEPROM. It's so slow. Well, fortunately, I have EEPROM from the future to talk about here because I ran the same script before. So if we fast forward till that hits 100%, we're going to see results much like this. We're going to see a flatness calibration and a YTF calibration. Now, the flatness calibration just adjusts the level of the signal on the spectrum analyzer display as a function of frequency. At each frequency, it adjusts the level of the signal a certain amount, so that the levels match up with what is shown on the display. Pretty straightforward. But a cool trick is that you can actually see this in the noise floor of the spectrum analyzer, because if you're the spectrum analyzer, having no signal, actually it always sounds the same, right? The noise floor from kind of the spectrum analyzer's uncalibrated point of view always is the same. It would be a flat line. It's only the adjustment that makes sure the signals are at the correct amplitude that moves the noise floor up and down. And so you can kind of see, you can see the calibration in the noise floor, which is a pretty nifty trick. But that's the flatness calibration, and the YTF calibration is going to be this thing. Oh, so the YTF is a Yig tuned filter. It's basically a bandpass filter that chops out the signals of interest. Not all the way. There's another level of chopping that's going to happen, but this is a crude level of chopping that makes sure that at the image frequency, 600 or so megahertz away for this spectrum analyzer, nothing gets through. That's very important, because the image frequency is ambiguous with the frequency that the spectrum analyzer wants to analyze. And so this chops the two away from each other, chops the two ambiguous signals into one signal, and makes that unambiguous. And this is what it looks like. And essentially there are two electromagnets here on either side, and suspended between them is a sphere of monocrystalline yttrium iron garnet, and that there's one frequency where that's a function of the magnetic field that it resonates at, and will plop the signal from one line to another, and that's the bandpass that you see. It's like the gyromagnetic precession happens at a frequency that you've applied to the input or something, and if it lines up, it'll be in your bandpass, and if it doesn't, it won't. And that's how the bandpass is achieved. And there's some crude steering of the bandpass, but then there's some fine tuning where we pick the precise level. And so the crude steering gets it in the ballpark, and then the fine tuning, the DAC here, gets it right. Lets us select right where our frequency center is, and we want to park it on one of the peaks here. And that is what our YTF calibration is all about. Now that we've successfully downloaded the EEPROM, we can see if our Back to the Future measurement was similar to what we were talking about. Yeah, it was. All right. Now let's write that to a file so that we'll have a good reference of what the EEPROM was while we were taking our measurements. Now we're going to open connections to all three of our devices, the signal generator, the power meter, and the spectrum analyzer. They're all reporting. Now let's go. Let's sweep that signal generator and take our measurements. It's going to take 5 whole hours. So see you in a bit.